Welcome to DoomConf August of 2022. It's nice to see some new faces in here. Well, faces. It's nice to see some new people in here, and yeah, we've got a great lineup this time. Um, not not Henrik's, not the sort of stuff, flashy new stuff, but a lot of interesting things here. When I mean flashy new stuff, I mean the Doom CLI stuff. That will be coming next month, hopefully. But in any case, we've got a really interesting talk. And yeah, let's pass it over to Gagbo, who's going to talk about making your own modules.
My name is Gerry. You can call me that. Giagbo is really, or Gagbo is really just a nickname because it's easier for me online. And we are here today to see why and how to create some private modules in your Doom configuration, either to share with the world or just to use for yourself. Before it starts, I really need a single disclaimer, I guess, that there's a new version of the CLI that is coming soon-ish, TM. For that, it will really only modify the syntax of the stuff that you use in your init.tel file, but everything that I'm going to talk about is going to be exactly the same otherwise. So you can, for the most part, ignore the fact that there's a new CLI that is coming and that has started coming from a little bit of time. Um, the other point that I want to pull is that the only prior experience that I need is that you need to have seen at least once in your lifetime how we install a package in your Emacs config, either from vanilla or Doom or whatever, but you need to get a rough idea of the process that you need to install a package. Um, if we have questions later about like my theme or my font or whatever, I can answer that later in the questions thread, I guess. So who am I? Before who am I? This is probably going to take around 20 minutes with 10 minutes of me talking and saying weird stuff and 10 minutes of me trying to live code a module. So who am I am Gerry, so Giagbo on Discord, on Discourse or GitHub or whatever, and Mosex on most other platforms. I have a blog. I am a very bad Guilty Gear player that is trying to main soul. And my experience with the modules is that I wrote and maintained the UI layout modules for the Bepo part, Bepo. And hopefully, once we get that PR merge, I'll start to also maintain the ligatures module. So before we talk about why you'd want a module, we need to talk about what is a module. And a module is really simple to understand. It's just a list of packages for Doom to install and some Lisp code to load when you start Emacs. So really, if you need to think about a module in a very bare bones way, there are two files. One called packages.yal that describes all the packages that Doom CLI must download when you run Doom sync or whatever. And one file called config.yal that contains the code that is loaded at the start by Emacs to configure the packages. So that's where you need to be careful about lazy loading and stuff. There are some extra files in modules commonly, but mostly you don't need to care about those. Like you can ignore them, and once you start having problem, you'll learn about their existence. So really, it's just two files. And the main thing that you can think about when you see those two file names is that you have the same in your own DOM configuration. And that's the main point that I really want to bring home right now is that your config is a private module. Like what we call in the documentation, your private module is that it's your config file with the config.yl and the packages.yl that you can have. And this private module is basically called the unnamed module as well. And it's really nice to have because you can always test your stuff in your configuration because it's your own module. And the other extra point that it brings is that it's always loaded last. So that's why it's the position where you need to add code to overwrite what Doom previously does, basically. Um, so with that out of the way, what are the reasons not to make a private module? Because it's really important to know when not to make a private module. And it basically comes down to you don't want to add extra complexity for no good reason in your configuration. So if you want to add a private module because you think you'll get some street cred by saying that you've made a private module, I can tell you that you're not going to. No one cares. The other thing is if you want to modify the configuration from another module that Doom already gives, you're going to have a lot of adherence and it's going to be really hard to make it work properly. So, for example, I have a bunch of org configuration that is very specific. And instead of trying to make my own module for org mode, I just in my own config.यल file put all the code there and I load it and that's it. Like if you really want to add extra config on top of something that Doom already does, you shouldn't make a private module. Your config.यल is a nice place to do that. Basically because handling load order and handling the hooks is going to be a mess. So you don't want to do that. The other point is you really want to keep your config simple. Everything that I'm going to make either right now or later in the talk is something that you can make in your own config, which is a module for all purposes. So there's no need to make it complex for no reason. So don't worry if you don't know how to make a private module or if you don't know why. It doesn't really matter if you don't have a good reason to do that. Which makes me transition to what are good reasons to make a private module. One good reason that I like is that it allows me to modularize some code that is seldom used or activated. So there are stuff that I don't necessarily want on all the machines where my Doom config exists. And it's pretty nice to know that I'm just one flag away in my init file to like switch that thing on or off. So it could be Lcord, it could be PowerShell or any language that I only use on my personal machine or on my work machine. Or it could be something like FZF when I tried to make a specific module for that. So the correct way to do this, to have a module or some code that you load only on certain machine or not on other machines, would be to use like Git branches and find the correct commit and revert some commits depending on the machines that I'm in or stuff like that. I'm too lazy to care about this, so having a single module to do that is a nice way to have an easy on-off switch that I don't need to go through my Git history to do that. So that's one of the good reasons to make a private module. One another reason is that it allows you to test some changes before proposing them upstream to Doom. So, for example, Elken and I did some tests, but I didn't want to go through with it. So it's mostly Elken that is shoehorning the effort right now. But when we're considering using Corfu instead of Company to have the completion in Doom. Corfu is something that is entirely new. It doesn't depend on anything that is existing in Doom configuration right now, and it's easier to just have your own Corfu module that you can switch on and off depending on when you want to develop on it or not. That's also what I did when I proposed changes to the ligature module to make the code a little simpler. So I replaced the ligatures module that is built in with Doom with the stuff that I'm working on to see if the API is okay and if I can make it a PR to make changes to Doom. So it's quite useful to make a private module when you want to participate to the development and share stuff upstream. The other main reason where you'd want to make a good a private module is that, for example, when you look at my mod line, you see that it's quite different from what is built in with Doom. This line is called telephone line, and it's one module that I made that configures the mod line for me with packages that are totally different and that allow me to have like a totally different look and feel with my Doom session. The thing is, I'm of course writing a lot of bugs, and when I write bugs, it's quite annoying. So being able to have a simple switch to disable and re-enable the other mod line that actually works is pretty important for me, and it's nice because it gives me the peace of mind that I know that if I totally destroy my session, I can always go back to it really easily. This use case of having those self-contained modules that you can install and uninstall very quickly is really something that the next version of the CLI wants to address, where you will be able to actually in your init.tl file, point to modules that are remote, and that is going to be really helpful to help share these modules basically. So if anyone wants to use my telephone line module, they will be able to, because it's going to be available on GitHub or on SourceNet, and everyone is going to be able to have it. So those are the main good reasons to do that. And we are actually going to shuffle all of those to try to kickstart right now a module that is going to use most of what Nicolas Rougier is doing with Nano Emacs, and try to make something that resembles a little bit. So here be dragons. That's the session where I didn't prepare much, so it's maybe going to fail. But I really want to show you like how I would go to make a private module, and to show you that it's pretty easy to make. So the first point to make a private module is that you want to choose a name. The name has two parts. The part with the colon is the category, and the part with the name is the name of the module. The category basically decides in which folder you need to put your stuff, and the name of the module is going to be whatever folder you want to put the module in. So to kickstart that, I'm just going to add a module in my init.tl in the UI category that I'm going to call Nano. And once I've done that, I just need to go to my modules folder, and I already created a UI subfolder, and there you can just create the folder that is relevant for you. So I know that it's going to be Nano, and I know that I'm going to need two files, one config.tl and one packages.tl. So I can already create those. I'm really a bad typist, so you'll have to bear with me. So I created this file, and I need to create, I don't know why I have this file existing, but don't worry about that, the packages.tl. So you can see that at the top we have the no byte compile T, because Doom has detected that I'm creating a module and that I really want to, and it has a snippet to make the experience easier on me. So Rougier. So what I really do is I'm going to use that superpower called reading, and we are going to look at the documentation to look at what we need to do. So the first thing that you want to do is to know which package you need to bring in. So that's why I stayed in the packages.tl on the left side. And I just want to find the place where the recipe is specified, and copy paste it and modify it to have the correct syntax. So I want a package statement that is called Nano Emacs, and I guess I can paste that recipe. I don't really remember the syntax, so maybe a lot of stuff are going to be different. Just to be sure, I'm going to pull my packages.tl to look at the recipe. So that should be fine. And now that I've modified both my init.tl file and my packages.tl file, I can run DoomSync. This is going to be the only time where I need to run DoomSync, just to check that it can find my package and correctly clone it. It's going to do a bunch more stuff, but you can ignore that. I just wanted to check that my syntax was correct, and the way to do it is that it's cloning and building Nano Emacs. I don't need to run DoomSync anymore. No, I'm just going to need to kill and restart Emacs a bunch of times. And the thing is, you can consider that the config.tl is basically the only place. You can consider that part of your init.tl when you look at the README. So anything on the README, maybe it's not big enough. Anything on the README that appears is and is supposed to go in your init.tl can go in your config.tl. So I'm not going to make you read everything that I've read a little bit. the main thing that I want to check is that when there's stuff that is called mandatory, I'm going to use that. And when there's stuff that is called mandatory, I'm going to check if there is any precondition that I need to make sure for stuff. So this apparently I need to call nano base colors and nano faces. And apparently I need to, if my Emacs has a theme or color scheme, which is currently my Doom theme right there, I have to make sure that it's loaded before I load the nano faces. And same with nano faces, I guess. So I'm just going to try to do this correctly. The main reason why this nano module is a little harder is that um, this package doesn't really follow the usual set that you want to do with packages of Emacs, I guess, and that's the extra difficulty that we need to make sure to avoid, basically. So what it means right here that we need to load the theme before nano faces or nano base color is loaded means that I need to find where in Doom the theme is loaded to be able to hook that at the correct location. And that's the part where it can get a little hard for you to find stuff. I know that there's a variable called Doom UI hook that is supposed to happen after the theme is loaded. The theme is loaded, so hopefully this thing is what I need. So I'll just add a hook to call the nano base colors and nano faces after this hook is initialized. So let's go. This is, we want to use package. I don't even know if we want to use package nano for that. Don't think so. We'll see. So I'll try use package nano. We want to defer it. And we want to add some config, I guess, where we add hook doom init UI hook, and the function is going to be lambda parentheses nano faces and nano base colors. I don't know if the other matters or not. And hopefully, once I've done this, I can just close that, restart Emacs, and we don't have any error, but it didn't load the nano faces for me, or maybe it does. The one thing that I really wanted to get and to see if everything worked was the mod line. So I guess if I try to call nano mod line right now, it doesn't exist. So that's the part where it's going to be a little messy for me. Config. I guess I won't defer that, and I'll just call require nano for now because I don't want to be bothered with all these issues. And kill, restart, and you're basically in my development loop. So all the warnings that you are seeing right now are warnings that are happening because I'm using some adventurous experimental flags regarding native compilation to make it happen asynchronously, and apparently we have some issues still regarding the words are complicated today, regarding the warnings that are happening when the asynchronous compilation is happening. So you can ignore all that, but because I'm totally sensing that it's going to be a really long time through a lot of debugging, I will want to stop the talk here because that's basically all that I wanted to show. That when you when you want to create a new module, you just need to add it in your init.tel file. You just need to add the package to the package.tel file. And once you've done that, you can just consider your config.tel just as some configuration that is open and where you can do everything you want. Ignore the warnings, ignore everything else. I don't want to go through too much debugging because it's going to be pretty long, I guess. But that's how you kickstart a module and how you make sure that you can have the experience that you want while keeping everything from Doom. That's all for me, and I'll stop sharing my screen and start looking at the questions.
Awesome. Thank you, Gerry, for that excellent talk. So at this point, we can take questions from the audience. So if you have a question, then feel free to turn on your mic or leave it in the questions thread, and I can ask it for you.
So I was crystal clear.
Well, I thought Yeet was going to read JP Trace's question on the
Yes.
question thread.
So
I think he deleted it, I guess.
Yeah, because I don't see the thread even on Discord actually. Don't worry about the noob question. You ask away, and anything is fine. Like the main conclusion that I want to give, basically the extra thing that I want to say is that the main reason there's no like PR for the UI Doom module, UI Nano module, is that it's a pretty integrated experience, and it's very hard to find the small pieces that any one person would want to get into Doom. So it's really hard to make something that is generic enough to be just added to Doom and have everything happy with it. So that's the main reason. And also, I didn't want to deal with the non-idiomatic Elise packaging that Nicola is doing with the Nano Emacs package. So that's the main reasons why it's not something that is really happening soon.
I have a question about basically your experience writing the Corfu module. Mostly that, I mean, Corfu, because it's like a completion UI thing, I would imagine that in order to like implement it, wouldn't that, I would guess that it would require like a lot of integration with other parts of Doom, which are, I guess, sort of the hard thing about writing a module sometimes is that if it's really good if it's like self-contained, but if it interfaces with a bunch of other stuff, I'm not really sure how you would do that in a private module without, I guess, having like a huge amount of like advice and stuff like that.
Yep, that's a good question. That's a point that I didn't bring up. I have in my private modules, I tend to have a whole section that is stuff to delete if I ever want to upstream the module. And the main reason why you want to have that is that you will need to replace some stuff in the config module, like the default bindings and the default config, where because and that's a little bit of the internals, but the way Doom works is that depending on the modules that you have active, all the stuff that is in the basic default config modules are just huge functions that are dispatchers depending on the features that you have active. And since the config module doesn't know about the new module that you are writing, if you need to, basically, when I started writing consult LSP, when I wanted to have my own functions to have the jump to symbol or to have the listing of all symbols using the LSP interface, all that stuff was already baked in Doom with specific bindings. And in my config.tel of my private module or of my own config, I had to override those bindings to use the function that I added myself. So everything regarding the bindings and everything regarding like, well, the default module, I guess, are stuff where you need to overwrite manually, either with advices or by adding stuff in your private config. That's why it's very important to remember that, like, in general, you shouldn't rely on the load order between the modules because it may change and it may break everything for you. But the one thing that is sure is that your own private module, like the unnamed module, your config, it's always going to be loaded last. So you can always make the override for the bindings and the functions there. and you can be sure that it's going to be fine there, and leave like your module to be self-contained. And hopefully, once it gets integrated, we'll have to go through other modules to make the dispatch proper.
Flugo asks a question. Are you making a political point in having NARF instead of Doom as your splash screen?
Yes, I guess. I mean, so for those who don't know, and I wasn't using Doom at the time, but before Doom was named Doom, it got cancelled basically, and it was named Narf for reasons that I don't know. But I really do enjoy the mouse screen that someone made at some point when we were talking about Narf. So yes, and also like I kind of like Narf better than Doom, but that's just me. So yeah, it's important for me.
Okay. Rigor asks, so he's at the moment sitting on the fence right now about how much config should someone have before they break something into a module. Would you have any insight on that?
I don't really. I think you can keep everything inside your config module. Really, like the only reason why I explore things in different modules, as I say, is for the stuff that are really adventurous, where I know that I can break a lot of things. Like you've seen that a lot of stuff got different when I tried to activate my nano module, and it's pretty nice and comforting to know that I'm one comment away to undo all the bad things that I've done. But if it's just some incremental changes that you make all the time, it's totally fine to have everything in your own private module. Like there's this load bang function that can just take any EL files in your private config and load that. So for example, even though I have a bunch of org configuration, it doesn't like bloat my main configuration file because I just have a load bang org config and it goes to org config, and there I can have like another multi hundreds lines of code file with all my personal org configuration. And I think that it's the better way to do things if you don't want to get extra complications for no reasons, basically.
Nice. And it looks like we've got one last question. This is from Brongulus. There are some sections in a module that are auto-loaded. What are those for?
So it's basically for performance reasons. When you can put all your function definitions and all your helpers in the config.tel files. It doesn't matter at all. The only difference that it makes is that when you start Emacs, Emacs will have to go through all the files with all your function definitions and parse them and activate the functions and do stuff. And that basically hurts your startup time for no good reason, because you don't know that you want to use the function right now, right there. So the reason for the autoload.el file is that if you have a bunch of function definitions, you can just put them there and it's not going to impact your startup time, but you're still going to be able to call the functions when needed.
Nice. Okay. Unless there are any more questions, I would like to say thank you again to Gerry for presenting today. It was a very good talk, and hopefully not too much of it will be outdated by the time CLI 3 comes out. Or we should hope for that, because then we get another talk from you. Yes. Oh, hold on. I might have let you off too soon. So Hilo asks, is it possible for one module to turn off other modules? For example, Nano Emacs might want to deactivate the Doom mode line.
No, it's not possible, because the way Doom loads is that it sees the names of the modules and it just loads everything. So if you want UI Nano to deactivate UI Doom, for example, which it should not happen because it doesn't seem that they are incompatible, but if you want to do that, you would need to modify UI Doom to check on load if the module for UI Nano is active or not, and then it means you need to upstream changes or whatever. So it doesn't really work like that. Sadly, you really need to check for that yourself. And if you want to have some automated checks for that, you can create another file in your private module called doctor.el, where you can add extra checks, and then Doom Doctor will tell you if you have incompatible modules that are active at the same time.
Awesome. Okay, now I think we're done with questions. Oh, Hilo's typing. We'll give him a second. Oh, he just wants to say thank you. Awesome. Well, now I can say thank you, Gerry, for a very good talk. Before we continue with me, let's get a little bit of housekeeping out of the way. I think Ricardo's stuck out there. So can I ask people who are near the entrance to sort of clear it? It's such a weird thing to ask that online. Let me see. In that case, what we'll do is we'll move on to me. How weird. I'm announcing myself. Okay. Yeah, so today I'm just going to talk a little bit about Flymake. If I can get the thing up. Moving to Wayland has meant that a lot of things have changed for me. That's my screen, and that should be good now. Okay. Yeah, so let me get up my notes. Awesome. So yeah, let's talk a little bit about Flymake. So let's start off with what is Flymake. So Flymake is a generic package provided with Emacs that provides diagnostics. It provides diagnostics within a buffer. So as I mentioned, it's included in Emacs by default and is a drop-in replacement for the main diagnostic package we'll use, which is FlyCheck. That's provided by the syntax module. Now, that brings up the question, what exactly is a diagnostic? Now, this may seem a little bit tedious for a lot of us, but I think it's worth going over. In short, a diagnostic is a piece of information tied to a part of your text. So the main example of this is a syntax error. Your linter will go through it and it will find let's say you messed up a bit of syntax, and it will tell you exactly from here to here, this is syntax I don't understand. But in reality, Flymake is generic, so it can be for anything, as long as you can run a command from it. So anything from your style guides to spelling mistakes to your manager's naggings encoded into a command line application. As long as you can run it, you can probably turn it into a Flymake diagnostic. So that brings up the question, why replace Flymake? Well, not Flymake, FlyCheck. That's what we're replacing it with. Well, in reality, if FlyCheck works for you, then there can be little reason to switch. A lot of people don't like shaking up their workflow, and I can understand that. That being said, some nice reasons to switch include it's built in. Less things to install, and because it's included with Emacs by default, that usually implies it will be maintained into the foreseeable future. It sort of composes nicely. Oh, actually, I've got little things. So it's built in. It composes nicely. And what I mean by that is instead of reinventing the wheel and introducing a new way to do things, instead of creating its own system of activation, all you're doing is you're adding Flymake backends, a simple function, to a special hook. If you want to make it mode local, you'll just use a local hook, and it's all Emacs you already know. This is in contrast to systems like FlyCheck. I'm going to mess that up quite a bit. This is in contrast to FlyCheck, where it's registered specially through FlyCheck functions and macros. Instead of creating backends through just a simple function that responds to certain arguments, you're using a FlyCheck macro, and so on and so forth. So there's less wheels being reinvented here, which is nice. It allows us to compose the eLisp a little bit more nicely. And oh, come on. It basically does not need to be configured. For this point, I feel like channeling our inner taco is needed, and we should all learn to love the defaults. But, you know, I make this joke sarcastically, but it's kind of true. For the most part, this is all you need. All we're doing is we're activating fly mode on most programming and text modes. You know, we're telling LSP mode, you know, use Flymake as your diagnostic provider, and then we're putting the indicators in the right fringe, and you're done. And you know, if you're just using LSP, which for most of us we are, you're done. You don't need to do anything else. You don't need to touch Flymake diagnostic functions. Not that you shouldn't touch Flymake, not that you should limit yourself to that, but it's done. That's what it goes back to what I was saying about it being a drop-in replacement. After that, I was back and working.
Yeet.
Yeah.
We've been looking at the first slide for the past 50 minutes.
Have we? I thought this is... Well then, that's entertaining. Give me a second. Okay.
Yeah, it's all good. Cool.
So now you can actually see what my config looks like. We're just basically adding a hook, setting a variable, setting a couple variables, and we're done. And yeah, like I said, it's pretty much drop-in replacement. Now, when it comes to actually using the thing, it's relatively simple at the same time. From the user's point of view, using Flymake is no different from using FlyCheck. They're all diagnostic providers. In Doom, all of your favorite commands automatically fall back to Flymake. This is thanks to Henrik and other contributors' foresight in the fact that they realized that these commands should be generic. I think recently Donatello actually included PR'd a fix to allow for us to use console Flymake and so on and so forth. One thing that is true, and this I'll go over this in a bit, but diagnostic descriptions, the actual message telling you why you're wrong, do show up in the echo area by default, but that's just a simple package away. So as I mentioned before, things like space CX, jumping between errors, all of this works by default in Doom today. And for the vanilla users in the audience, things like setting the next error function variable and calling console Flymake in your config is relatively all you need to do. This is not earth-shattering. It's quite nice. So yeah. So now we move on to a little bit about configuring the thing to make it work for you. You know, adding your own backends is simple. Just add hook, Flymake diagnostic functions, your backend. This is fine because backends fail silently, which means that you can include them all on Flymake diagnostic functions and it'll be fine. Now, of course, we wouldn't want to do that unless our backend is generic enough. So in reality, we will just use a local hook. In this example, I'm attaching it to, you know, X major mode, and we're just attaching it to a local hook. This pattern is actually so common that many of the Flymake packages you will see, I'll show you a couple in a minute, will just provide a function that essentially encapsulates this, which is nice. Now, I realize I've gone through this much quicker than I intended. That's fine. Yeah. So we've talked about adding our own backends, but now let's talk about writing them. Again, it's a relatively simple process. If you want an actual annotated real-world example, the manual has a great example there. And I highly recommend you read the Flymake manual because it's a very good overview of the entire package. It's not big, so it should take you about 10 minutes to read from cover to cover. But the basic gist of what a backend does is you're going to take the buffer that you're in, you're going to pass it into a set of lists. Then what you'll do is you're going to construct a bunch of these diagnostics. using Flymake make diagnostic. You'll pass in the buffer, the region, the type. So is it a note? Is it a warning? Is it an error? And then what actually went wrong? What's the message? And then finally, you will pass that list of Flymake diagnostics into a report function, which was passed in from which Flymake actually passed your diagnostic when it began. And that's about it. Again, this is a very high-level overview, but, oh, someone's coming in the door. Give me a second. It would not be DoomConf without a few interruptions. In any case, it's a relatively simple process to write your own. This is, again, a very high-level overview, so do check out the manual. It is a meta X info away. Now, this finally brings me on to the downsides. Before I start talking about the downsides, I will say that the FlyCheck team have put up a comparison on their site. In short, this is propaganda by Big FlyCheck. That being said, there are a few things. If you saw my hand go up, that's my brother being annoying. So, unlike FlyCheck, you have to write the function by hand. So I showed you this. If I actually switch to Emacs, I can show you what an actual one looks like. Or I can just switch to my browser. Where's a little tidbit? That's not what I wanted to do.
Is that all the paint inside?
No.
Well,
Where is it? No, not that. There we go. Share. And now, if I switch over to Flymake shell check, for example, this is what an actual checker will look like. So basically,
we are seeing. Sorry, we're seeing your view of Gaviton.
Still seeing that. A single window. Let's have a look. Share. Is it sharing now?
That's a browser.
That's a browser. Where am I now?
There's eLisp.
So we're basically going from here to 115. Essentially, what you'll have to do yourself is manage the entire process of whatever you're calling. So here we're making the process for shell check. And then essentially within this process Sentinel, we're actually managing what happens. And within this large CL loop, we're actually creating the diagnostics and then finally passing those diagnostics in a list back to the report function which Flymake provided for us. So in a sense, it is a little bit more complicated than just your basic thing. So there is no declarative interface like FlightCheck. In FlightCheck, it's much more simple. That being said, it's not like it can't exist. It can. There are certain packages that do allow for it, such as Flymake Easy, but that is not included by default. Another one is that there is no concept of a dependent checker. So in FlightCheck, you will have checkers that run in a certain order. And they report back, and they will report back in that order. If you've got a checker that needs to run first, like a syntax checker, that will then be passed into a linting checker. That is possible in FlightCheck. That's not terribly possible in Flymake. Again, it's eLisp. You can do whatever you want, but all backends are run in a non-deterministic order and will report back asynchronously. So there is no next checker, if you will. Personally, I've never used this, so I don't miss it, but it is worth considering if you do have a workflow that does that. Now, this is probably the biggest one, but the underlying data structure that Flymake uses to hold these diagnostics is overlays. So if alarm bells aren't ringing, then it should. A lot of diagnostics may freeze up Emacs. Now, personally, I've had over 50 diagnostics in a buffer and it's been fine. I'm sure it will scale somewhat. And eventually, when overlay performance is fixed, it should be fine. But for now, it is something to consider. Let me switch back to my slides. Where is the thing? Here. Beep, boop. Allow single window. There we go. And you should see my thing again. And now, yes. And knowing me, there's something else I'm probably forgetting. Your workflow will be different to mine. So yes. Finally, there's a call to action here. So I am currently working on a pull request to integrate Flymake into Doom. I don't want, Flymake already, you don't need to think about it, but now I want you to think about it less. All you have to do is add a flag and you'll get all of these goodies for free. The reason why we're slowly moving towards Flymake within Doom is that is because it is first of all built in, and overall we should move towards built-in packages for reasons I think we will discuss later, but it also means that you get all these goodies. So if you have a checker that is not included by Doom, then send it to me. You know where I am on Discord. If you have a workflow that you want to replicate, then let me know and we'll start working on it, and so on and so forth. Again, I don't know if my slides have caught up, but that's all I wanted to say. If you want to check out the PR, it's a stub at the moment, but it is PR ID 6660. So quite a nice number there. But in any case, that's me. And yeah, that's me. So I know there are a couple of questions. Yeah. 2 hours. Okay. So now Brongulus asks which of the two are more performant, FlyCheck or Flymake. I haven't done any benchmarks, so I wouldn't be able to tell you. Feature-wise, FlyCheck probably has a few more benefits to it. I might as well just show you what I'm talking about. Oh, there we go. Allow. I'm still getting used to the new Wayland dialog for something. Where is it? Flymake.org. Yeah, we'll share this. So that should be Emacs right now, displaying this presentation, in fact. And essentially, what we have is, I'm not sure if that's showing up. Is it doing the thing again? Probably is. Allow Flymake, no, wrong one. Flymake.org. Okay. Is it updating? No. This is going very well. Yes. So while my computer is being annoying, I can answer some other questions. Brongulus, I'm not sure about your question. I haven't noticed any performance dips. There are, I wouldn't say there's necessarily any feature benefits. FlyCheck can do a lot, but at the same time, these are diagnostic packages. These are not necessarily the most complex of things. So any features FlyCheck does have could be replicated. I think the biggest one is probably going to be the dependent checkers, but again, that is, your mileage may vary. So Also, anyway, so Rigor asks if it competes with LSP. It does not. It actually meshes quite nicely. Essentially what you would have, and if my screen sharing was working, I would be able to show you exactly how it worked. But essentially all LSP does is it provides a backend function like any other backend, and that's how it gets diagnostics into the buffer. That's why I said it worked kind of magically. As long as you set your variable and you've done that, as long as you've set the variable to tell LSP to prefer Flymake, it should be fine. So the relationship between LSP and sort of diagnostic packages in general, LSP doesn't do anything itself. Language server clients don't do anything necessarily themselves. What they would do is they talk to a language server, and then they would go back into the client, and then the responses from the server would come back into the client, and then the client would decide on what to do with those. So in this case, when we're talking about LSP, what LSP will do is it will register a checker with FlyCheck if you're using that, or a backend function with Flymake, and then the diagnostics it receives from your language server would then be formatted into Flymake diagnostic, or whatever data structure FlyCheck uses, and that would show up. So it's essentially using the Emacs UI interfaces as its front end, if you would. Egglot actually uses this. Egglot takes this to the sort of, not to the extreme, but Egglot exemplifies this more. Egglot doesn't introduce any new UI features. It just uses ones that are built into Emacs. So in this case, it will use Flymake for its diagnostics, while it will use capf functions, completion at point functions for its completions. Emergency. Now we've got a emergency poll of whether we say egglot or eglot. I'm going to continue saying egglot for the time being. Okay, well, I guess I've lost that debate, so...
Democracy.
In that case, I'll be now saying eglot. So in this case, eglot turns this, exemplifies this more. To jump to certain definitions, it will use xref, and so on and so forth. In a sense, eglot is just the client, and that's sort of the relationship. They mesh quite well together as by design. So hopefully that also answers Nano's question along the same lines. I feel yes. Yes, that's actually quite, I've seen this before, and it's quite a good diagram on how this works. So do check out questions, because Gagbo has made because Gerry has made a very nice diagram, and it is not shitty like he says it is. In any case, I don't think there are any more questions. Sorry about the sort of haphazard nature of this talk. I didn't realize I'd have quite so many issues, and the timing of my family coming home was quite something. But in any case, yeah. Well, now what we're going to do is we're going to take a quick 10-minute break, so that people can get water and so on and so forth. And yeah, so let us return in 10 minutes or so. So that would be 3:13 for me. I'm sure you can all add 10. But yeah, thank you all.
But yeah, I do wonder how hard it is to get the presentation working on Wayland, because on KDE, speaking of French there, on KDE, you get the prompt, and I actually got the prompt twice, and I just accepted everything twice for everything, and it ended up working. But I do wonder how it's working with GNOME or something else. But yeah, Wayland does hurt a bit when it comes to sharing screen. That's sad.
It still doesn't work for Discord. At least I haven't. I haven't been able to get it working yet. It's been quite a while now.
I think I was able to make it work, but like I went through the Flatpak install of Discord, because the Flatpak knows that it needs to pull the Portal packages, and the Portal packages know how to talk to Pipewire, and Pipewire then knows how to get the relevant parts of the screen. Like it's really complex, but you can like invoke the correct daemons and get it working.
In general, I got it working in Firefox with various daemons. But my Discord is standalone, therefore is running Chromium, and I haven't been able to get anything related to Google products like working with screen sharing at all since I switched. They don't want to cooperate.
Yeah, fair enough. Might be the case.
Okay. Okay, great. Yeah. Hi, I'm Monad. Don't be intimidated by the fact that this talk is like the third one in a series. They all kind of relate to each other, but given the fact that not all people can like make. Oh wait, does Yeet need to present me?
I was, but then I realized that you sort of got enough energy to sort of present yourself. In any case, welcome back, everyone.
Yeah,
this is
and
Mona. Going to talk
shouldn't
about.
be master. That's like an excellent
Over to
way.
you.
Yeah. Okay. I'm just going to continue. Yeah. So don't be intimidated by the fact that this is like talk 3. All of the Relativity for Non-Physicists talks are kind of meant to be standalone. Hopefully, like by listening to them like in a row, you maybe get like a bit of like a better understanding. But you know, like I don't necessarily expect you to have listened to the previous ones, but hopefully it will be as easier to understand if you did. When it comes to questions, following Flugo's excellent advice, I'm only going to be looking at the questions channel for the duration of this talk. And also tag me just to make sure I don't miss it. With the previous talks, I think, well, the first one has been recorded and is uploaded in the place. The second one, which was last time, there were like a bunch of recording issues. So I think that maybe there's like a partial recording or something, but currently it doesn't really exist, unfortunately. Anyway, so the agenda for today is to talk about tensors. What are they? Why do we care about them? Finally convincing Rigor to stop wanting to kill me for putting this off for so long. All those good things. When it comes to the expected background for this talk, we're not really going to, you don't really need to know much, just general like math notation. It would help if you knew basic linear algebra, what derivatives are, but like none of this is really core to what I'm going to be trying to get at. It all has to do with how much you are willing to believe random things I say, and without justification, I will try to give as much as justification as the format allows. But if you're not really a math person, and you can just take me at face value, and hopefully you will still get something out of this talk. So what are tensors? Here's the boring versions. You have some vector space V, where a vector space is the usual mathematical definition of like a field over a set, that sort of thing. A tensor is just a multilinear map from a bunch of copies of the vector space to R, where V star is a dual space, which is included for completeness, but you don't need to care what a dual space is for the purposes of this talk. It's basically like a slightly different version of the vector space. And if you ever did anything with matrices, it's basically like an n-dimensional matrix. It's just as simple as that. This is the boring version because even though it's technically correct, it doesn't really get at the core of what like tensors are as a class of thing in physics, which is what this talk is about. I'm talking about tensors from like a physicist perspective. I don't know if mathematicians have like a radically different view on these things. Maybe that's a question for Flugo later. Yeah. So the first bit of background and actually the last bit of background, never mind. The first bit of background that we want to talk about to understand tensors is group theory. And before we get into like the details of like what a group technically is, we want to know our motivation as physicists of why we care about groups. The reason why we care about groups is that interesting coordinate transformations basically can be described using groups. When you describe the universe, like we have like several different choices of like how we define our coordinate system. You can have the center of your coordinate system be like in Paris, it can be in New York, it can be in Jerusalem. And all of those will be like valid descriptions of the universe in a sense. Because we have different coordinate systems we can choose, the way that we transform from one coordinate system into another is something that we also need to understand if we want to have a consistent description of the universe. Like easy examples of all of these transformations are things like rotations, translations, reflections, things that basically change your perspective. And basically, since we do have choice in our coordinate system, we want to study in what ways our choice matters, because we could choose coordinate systems that basically make physics incomprehensible, and we could choose just the exact same. Hopefully, we can build an understanding of different types of coordinate systems that relate into each other in an understandable way. Since we're talking about transformations, we're going to want to generally talk about groups. A group is essentially have some sort of set G, some operation that we usually denote with like a multiplication thing that takes two objects from G and returns a third object from G. This operation needs to have a few properties, associativity, which means that if you chain a few of these together, it doesn't matter in what order you chain them, it's all the same. There needs to be some sort of identity element that does nothing. And there need to exist inverse elements that allow you to take an element and return the identity element. When it comes to like a generic like operation that takes two things and returns one thing from the group, all three of these are like fundamentally optional. Like you can take away any of these or any two of these or whatever and still get some sort of structure. There's like this cool, actually I probably should have put in the presentation, but there's this cool diagram that you can see all the different names for the different stuff. But when we talk about transformations that interest us as physicists, we generally want all three of these. Why is that? The associativity is just kind of something that things get really weird without. Essentially it means that the order in which we do the transformations really matters. And when we look at transformations that are our initial motivation for this sort of thing, they all can sort of like compose. Like if you move twice, it's going to be the same as like moving 3 times but in shorter bursts, or doing one long move and stuff like that. So we don't want the order to matter. And obviously when it comes to transformations on our coordinate system, yeah, Gagbo is right, that's probably what I mean. And when we talk about transformations on our coordinate system, we always have the option to do nothing. So we have to have an identity element. And generally when we do something, we also need the ability to be able to go back, because otherwise the lack of an inverse generally means that we have lost like something fundamental about our description of the universe if we can't go back. If we preserved all the information we need, we should be able to do the reverse operation, which is why it's as physicists, we generally assume that we have an inverse element. So let's go through a few examples. The easiest one is the translation group. We have 1D space with it. We have like R, the real numbers, with addition, and the identity is 0. So you add any two numbers, you get a number, you add 0, etc. Similarly, you can do this for 2-dimensional space, where you just add the first element to the first element and the second element to the second element. You can also do it with n-dimensional space. It's by far the simplest example. You can also do rotation, which is basically the same thing. Instead of having all of the real numbers, you just have all of the angles, so numbered between 0 and 2 pi. You add them modulo 2 pi, and the identity is still 0. You can also have a subset of all of the relevant rotations. For example, the rotations that preserve a square, which are basically rotating by 90 degrees. You can also have rotations because even though we start from a motivation of describing transformations of space, but we don't have to. A group is like an abstract mathematical thing. We can also just do, for example, multiplication with identity 1. There's no real reason to okay. For the Flugos in the audience, assume that we're excluding 0 here. I forgot that when I wrote this, but 0 doesn't have an inverse. So for this to be a group, we can't have 0, but that's not interesting for our purposes. Multiplication doesn't really have like an obvious geometric meaning. I'm sure you could figure something out that would be super cool, but in general, like our coordinate transformation is our motivation, but from that motivation we get to an abstract mathematical thing, and then we go back to original motivation with hopefully a better language to describe things. You can also get really, really abstract, like invertible functions. You take a function, if it's invertible, then we satisfy that, and then we have like functional composition between functions, which satisfies all of the properties. This is also a group. It's kind of, we're starting to get into objects that are not really related to things like points in space, but a group is a very general thing. And a lot of times physicists might sometimes ask, like, what are the values of like delving into group theory? Because it's right that when we talk about tensors as physicists, you could ignore all of this stuff and just talk about rank n matrices. Like, why do we want to do this abstraction and learn about groups like that? So the thing about abstractions, good abstractions, which hopefully you all know as people that program and try to find good apps and try to abstract over APIs or whatever. A good abstraction extracts the essence of whatever it is you're talking about, and hopefully by choosing if groups are indeed a good abstraction, we have extracted the essence of what we of whatever we are translating of the coordinate transformations we're trying to talk about. For example, for translations, for the translation transformation, we extracted a really subtle thing, which is there's a difference between the points in space and the transformation for the points in space, because there is a big difference. There is a big difference between R and Rn plus. It's not just like, oh, we took the same R and we added a plus. There's like a fundamentally different thing between the points in space you're talking about and the fact that you can like shift those points around. Just because you're talking about shifting those points around in the same language as the underlying points themselves doesn't mean that you're talking about the same thing. And by talking about groups in the abstract, you can make this really clear. This is, right, and we can make this like separation even more explicit by talking about what we can call like group action on sets, which essentially we have some sort of set X, we have a group G and operation, elements in operation, and we have an action that basically takes a group, an element from the group, and an element from the set, and gives us back an element on the set. Essentially, we use the group to transform the set itself in a totally separated manner. And the way that we do this is that we make sure that the action respects the group structure, which means that the identity does nothing, and composition of functions basically makes the elements act one after the other. So here we have the set is R and the group is R and plus, but we have separated out the two R's because they don't really need to have anything to do with each other. Other slightly less redundant examples of this could be things like a sphere and rotations, because a sphere is like a subset of points in 3D space, and rotations are going in 3D are going to be represented by two angles, or you have like a one sphere when you have one angle. And there it's obvious because the spaces are totally different. We have the example that we talked about earlier about translations and about R and translations, and we can also do something that's random and not like super called for, which is like a ball and reflections, right? Because a reflecting operation like takes all of your points and flips them around, and if you only choose like one axis to reflect over, essentially have two elements in your group. You have the identity element and the reflecting element, and reflecting is its own inverse. Essentially, we want to really make sure that when we talk about transformations, we're talking about them as something that is different from the points we're trying to describe under the surface. Are there any questions about like the details of group theory? Not necessarily why do I care about this, because that's the next part. because before I move on to the next portion of the talk. No, cool. Okay, so the next point that we want to try and build up is the concept of symmetries and why they're important to physics. The important thing about symmetries is that they preserve structure. They're not just like random transformations. Like they're symmetrical in respect to something, and whatever that something is some sort of underlying important property of the universe that we care about. A simple example of this, of like what kind of structure you could preserve, is a rotating cube. Here you can have like rotation symmetries, and every 90 degrees, you're going to get something that preserves the cube structure. The cube looks the same. Other transformations are don't preserve the symmetry of how the cube looks like. So you can have like a bunch of random transformations that don't give you anything useful. But if you have ones that preserve your structure, you can generally learn a lot more about your structure or force properties about whatever you're trying to calculate. And physics is essentially a structure that we build over space. We have our description of space, R3, like all of the points in the universe that we want to talk about and understand what's going on with them. And on top of this, we overlay some sort of structure to describe things. For example, we can overlay a temperature structure, which is a function from every point in space to a number between, somewhere and somewhere. Temperature can be thought of as a scalar field, and it is some sort of structure that when we transform our coordinate system, we will also have the question of how does temperature transform. We can also have more complicated structures, like an electric field, which instead of having just a number at every point, we can have a 3 vector at every point. It's very important. The arrows here are wrong. Never mind. It is very important that the two R3s in the electric fields, to remember that these are unrelated. The first R3 is our points in space. The second R3 is just some sort of three-dimensional. It's just a three-dimensional vector space that we use to describe values of the electric field. These are like two separate things. When we talk about like physical interactions, like we can relate the value of the electric field to our points in space and that sort of thing. But when it comes to like what is going on in this description, these are separate. They're separate three-dimensional spaces. We can also talk about point particles, which are not as clean mathematically as just functions from space to somewhere else, because point particles only exist in like one location, but that is like mathematical details you can work out. It's not like the essence of the thing. So at this point, we want to ask ourselves, what transformations preserve physics? When we talk about preserve physics, we want to mean like keep the laws of physics the same. So even if we don't know what is like the original coordinate system, we still have the same description of the universe. Because whatever these transformations are, they will tell us a lot about the type of physics we are allowed to have. The way that we get these is from Newton's laws, which I think I've mentioned in some way or another in every relativity talk, which is funny because it's supposed to be about relativity. But Newton's first law is where we more or less get this. We get the idea that with no outside forces, objects move at a constant velocity, which is basically straight lines in space-time. When you have location as a function of time, it's only like a linear. It's only like a linear function. And you can ask ourselves, what are all of the symmetries that preserve straight lines? And the ones that we care about are essentially translations in time that move the time by some constant amount. Translations in space move space by some constant amount. Rotations, where I hide all of the details of what a rotation is in a matrix, but in your head, I'm sure you have a view of what rotation looks like. And moving at a constant speed, or this is also sometimes known as a uniform motion. For why, if you want to ask like why these preserve straight lines, you can do the math. I'm not going to do that right now because I did that at previous talks, and this is a point where you kind of have to trust me in the interest of us moving along. And then we have like Newton's second law, which basically looks like this is like F equals ma, where a is the second derivative of the location. The fact that it's a second derivative has some interesting implication about like solving the equations of motion that we don't super care about at the moment. But the important thing is that because f is f of x is equal to x, we get the idea that f needs to transform like x transforms. Because if it transformed differently, then this equation wouldn't hold, and then we wouldn't be in a physics preserving coordinate system. For example, in previous talks, you might remember the bit about non-inertial coordinate system. Well, if we only care about inertial coordinate systems, we only care about coordinate systems where physics is preserved. So physics which we get to by coordinate transformations that we talked about previously. And this transform similarly thing is the essence of what a tensor is, essentially. We just want to generalize it a little bit. Essentially, we have scalars, which are rank 0 tensors, which stay exactly the same in different coordinate systems, sort of like mass. When you change a coordinate system, the mass of particles won't change. You can also have 1 tensors, which transform in exactly the same way as space, which like a force in Newton's second law. But we can generally just abstract this over to n dimensions. We can have like a high order combination of vectors, like an outer product, if you're familiar with that in math. Just a bit more detail on what like this higher order vector stuff is, if you haven't seen them before. A vector is just a collection of n numbers. So we can have like fi, where I is like a sub-index going from 1 to n. And all of these numbers can, and if you have like 3 numbers, they they can correspond to a direction in 3D space, or n numbers to a direction in n-dimensional space. And if you have a matrix, you can do this by combining 2 different numbers with 2 different vectors with 2 separate indices. For example, you can take the electric field with the magnetic field and create a matrix out of them by basically having 2 spatial directions in your description of the tensor. And similarly, when you rotate space to a 1 vector, when you rotate space, a vector just rotates exactly the same. When you have a matrix, you just need to rotate both of the indices in the same way. So if you write down all of the math for like how to do the space rotation, you basically just have like a rotation multiplied by another rotation, which overall makes the structure transform in a more complex fashion. But you're still just acting on a rotating. Wait 1 moment. But you're still just essentially applying the rotation, like the rotation transformation to the tensor. Okay. Rigger asks, should I understand transform similarly in a sense that f vector and x vector are pointing to the same space? No. You should understand that if you, for example, okay. Rotations are a bit complex to talk about without equations. So let's say that for whatever reason, we're interested in multiplying the vector by a set number. So if x goes to 3x, so all of the distance becomes 3 times as large, then all of the forces also need to become 3 times as large. That is what I mean by transform similarly, because here they essentially have to satisfy this equation. So whatever transformation operation we do to x, we also have to do to f. So this holds. But this is like a mathematical connection. It's not like, it doesn't necessarily have to mean that both of these represent the same vector space, if that's what you mean. If that's not really what you mean, then come up with a mic and ask the question. Maybe that'll be easier. Okay, Rigger isn't coming up with a mic, so I'm going to assume that it's fine. Okay, Gagbo asks.
No, I'll work on a better question and go on. That's answer, Gagbo.
Okay, Gagbo asks, in which conditions does the force F and F equals ma only depend on the position? I'm used to having boundary conditions that also change F. Well, that is a good question. I think that generally, when we talk about forces in the abstract, they think they can only... I think that fundamentally forces might only be able to depend on your position. They could definitely only depend on either your position or your velocity. When you talk about forces that depend on your velocity, all of the common examples I can think of are like effective forces like air resistance, which don't really count when you talk about fundamental symmetries, because air resistance isn't like a fundamental theory of the universe that we want to base our symmetries off of. It's like an effective description of a bunch of thermodynamic effects. And I don't really think that Okay. The thing is, the reason this question is a bit hard to answer is because when you get into like very fundamental descriptions of the actual universe that we talk about, we tend to not use forces anymore for reasons that will hopefully become a bit, well, actually, which for reasons I will explain why sort of at the end of the talk. So I can't guarantee that that when we talk about fundamental interactions, f can't really depend on velocity. But even if it depends on velocity, that doesn't necessarily matter that much, because velocity is one vector with relation to location. So the inputs of the force will still transform in the same way, and the overall force will still have to rotate or translate or whatever in similar ways to the location. So the point about the symmetry still stands. When it comes to if f can never depend on the velocity, I don't have like a super strong answer on that. I need to.
I mean, that's, I'm sorry, like the better way to ask my question, but I guess I'll see that later as well, was that it seems when you put the prem like that if f needs to transform similarly to x, it's because you have these equations that needs to hold with respect to symmetries, and the boundary conditions, they make it so the force does not depend linearly on the position anymore. And that's the point where I'm like a little weirded out.
Yeah. Okay. The fact that f is a function of x is not like the important thing in this equation for now. Like, it's important in a bunch of other areas of physics. But when we talk about symmetry, like the fact that f needs to like transform the input to a different way, it needs to transform the input x into something else. Let me collect my words a little bit. F does not have to be like a linear function of x. F can basically have whatever dependency on x that it wants. But it has to preserve the fact that if we rotate our coordinates, f also rotates, which heavily restricts the type of interaction that we can have. But when we talk about things like boundary conditions and stuff like that, then the boundary conditions rotate along with you. So that sort of ends up more or less ends up canceling out when you in your description. The main question is, after we rotate the universe, is f equals ma still like an equation that governs particle motion? And for that to be true, we essentially have to say that if we rotate x 90 degrees to the left, f also has to rotate 90 degrees to the left. Even though, as we said previously, f does not like live in physical space. It lives in like its own R3 space. It's just x and f have to transform in a similar way when we do coordinate transformations. Gotcha. Okay. Rigor asks, I guess I'm missing the difference between transform similarly and linear transformations. Well, okay. So the reason why I say transform similarly, well, I guess, okay, that's slightly bad wording on my part. I think essentially, if x transforms in a certain way, f has to transform in the exact same way. The reason why I say transform similarly is because when we get to like higher order tensors, then because x is a vector and a matrix is like a 2 vector, is like a rank 2 tensor, it doesn't transform in exactly the same way, but it needs to essentially have each of its vector components transform in the same way. So yeah, that may have been like not the best wording on my part. Okay. Right. So okay. So we talk about why tensors specifically. Essentially, we want to say that for our physics preserving transformations to mean anything, our descriptions of the universe have to be well behaved. When we have, because not everything in the universe can just be described as a vector that has literally the exact same transformation. Some of the objects that we use to describe the universe are more complex. So we need these objects to essentially, we need these objects to be able to transform in similar predictable ways. So eventually, when we eventually relate them to location using like higher order linear equations and stuff like that, or for all of the components that have the dimensionality of a vector, in a sense, transform like vectors, and all the higher dimensionality, and this way, all of the higher dimensionality components can also transform in the same way. Essentially, this means that like for an object that we talk about to have physical meaning, it has to if we want to have a concept of a physics preserving transformation, then it's almost like a tautology, but all of our description of physics has to transform in a well-behaved way, so we can extract scalars, so we can extract like invariant things from our equations, essentially. Speaking of invariants, as a side note, when you want to like describe our systems and in ways that give us like real meaningful information about the universe that isn't dependent on our coordinate system, We want to talk about invariants. We want to talk about things that stay exactly the same at every after coordinate transformations, because our coordinate system is a choice when it comes to how we describe the universe. And other than philosophical stuff like the fact that, are we describing the universe, or are we describing like a model that only approximates our universe? If you like putting that aside for a moment, if we want to talk about things that are like actual facts about the underlying universe, we can't have those facts be dependent on our coordinate system, because we can change our coordinate system. So, for example, an absolute location, of an object is not invariant, because we know that our physics is generally symmetrical to translations, and the absolute location will change. But a relative location, the difference between two different objects is invariant, because rotations preserve it, translations preserve it, and moving at a constant speed also preserves it. So the distance between two objects is like an actual feature of the universe that's important, that things can actually depend on. This is why when we have like f equals ma, or the second derivative of x, both f and x are vectors. There are things that will change according to our coordinate system. So they are very very useful linguistic tools to talk about things, but we can't actually. But they don't relate to like underlying important features of the universe, which can basically only be invariants. We can construct invariants from tensors. For example, you have a vector, and if, say, we had a vector and we only cared about rotating that vector, if we took the length of that vector, that would be an invariant. The absolute location versus relative location is basically that, except for other than rotations, we have translations, but it's a similar thing. So because tensors have well-behaved because tensors have like very predictable and structured transformations under our symmetry groups, we can use them to talk about complicated things, and then at the end of the day, we can construct invariants out of them, which is where we get our like underlying like important features of reality from. Which brings us to the idea of changing symmetry groups, which is where I bring this back to actual relativity. So there is only really one difference between Newtonian mechanics and relativistic mechanics, and everything else is just byproducts of this, and that is the fact that we changed our underlying symmetry group. When it comes to Newtonian mechanics, we have a group called the Galilean group, and we just change it a bit, and we get the Poincare group, and that's it. Like all of the weird paradoxes that you hear, and time passing at different rates in different places, and that sort of thing. All of that is just has to do with changing our symmetry group of the universe, because the symmetry group that physics is invariant towards is like a really fundamental thing with a bunch of knock-on effects. Note that this only talks about special relativity. General relativity is a bit more complicated, and I would have to think a bit more to say if just changing the symmetry group is enough there. I don't really think it is, but that is kind of outside of the scope of this talk. So what is the Galilean group? Similar, it's basically what we said earlier about symmetries that preserve space-time. Straight lines. We have space-time translations, we have rotations in space, and we have uniform motions. And the only real difference that we have between this and the Poincare group is that we switch uniform motions for something called boosts, which is essentially a way to add velocities that keeps the speed of light constant. So the more you add different velocities to each other, the sum of two velocities is always going to be a little bit smaller than their mathematical sum, because as you get faster and as you try and add more speed to your car, you're getting closer and closer to the speed of light, but you aren't actually getting to the speed of light, because part of the deal of relativity is that you essentially can't do that. For more details, see previous talks, basically. Mathematically, you can see that uniform motions basically have a very simple mathematical structure of time not changing at all, and x going to and our location basically changing over time. But boosts, in order to have all of the relativistic properties of things like keeping the speed of light constant and stuff like that, essentially we have to mix space and time a lot more, which is why it's like a fundamentally different type of thing. And this is so essentially we need to find a new version of physics that instead of behaving well under the uniform motion transformation, we need to find one that behaves well under the boost transformation. And this is essentially like the project that you have to do when you figure out special relativity. You need to like figure out how physics works again. You need to like convert all of your tensors from the old type to the new type. Now, it's a bit of a bait and switch because we sort of end up ignoring the time transformations in the Galilean group. The reason we do this is that if you look at it again, when it comes to time, we just have things need to be symmetric to translations in time, which when it comes to like more complicated structures is basically always going to be everything looks exactly the same. It's like a one-dimensional group translations by one parameter. So there isn't like a whole lot of like tensor structure to work with there, I don't think. And the other thing that we have is like space rotations, which don't really touch time, and uniform motions, which essentially only express themselves in the spatial dimensions. So we can basically ignore time as like a meaningful part of our coordinate system, which is why when we talk about Newtonian mechanics, we always talk about like three-dimensional tensors that take in time as a parameter. But we need to convert these into four-dimensional tensors where time is one of our actual fundamental coordinate system over which we want to describe our tensors, because it's now like a much more active part of our group transformations. So just to go through like a few examples of this. So the easiest one is location. We take our three-dimensional location and we move it to a four-dimensional space-time location. Obviously, and this is going to be a well-behaved tensor under everything else. It's very four-dimensional. The four-dimensional location is also a tensor under the Galilean group, basically because of the fact that time doesn't really do anything there. But because the regular location can also be a tensor over the Galilean group, and the fact that we don't really care about time in that way, we don't really use it. So most of Newtonian physics is built only around space coordinates. But when you move to relativity, we have to like add time as an extra coordinate. We also have the classic example, which is going from only talking about momentum to talking about energy and momentum together. The arrow is only supposed to be over the P. Essentially, when you talk momentum it's outside of the scope of this talk, but essentially momentum is a structure that like very deeply relates to translations in space, and energy is a structure that relates to translations in time. And talk about the Galilean group because we can very easily just ignore time and only talk about space translations. We can very easily talk about the momentum by itself. But when you move to relativity, we have to talk about energy and momentum together because they end up mixing with each other a lot more in boosts. Because when you only talk about uniform motion transformations, energy stays exactly the same and the momentum will change, but in a not very interesting sort of way. We also have slightly less trivial. We also have more complicated examples, like the electromagnetic field, where we essentially have like two vectors and we have to combine them to like a second order, like rank 2 tensor type thing that is way too complicated to write out here and and the details are not really meaningful enough for us to bother. But essentially, we can see that we have like a few general strategies when it comes to like tensor conversions. We can either take like a 3 vector and what is essentially a scalar under spatial transformations in a lot of ways and get a 4 vector. This isn't guaranteed. You have to have like good theoretical backing, but it is a pattern that comes up a lot. And if you take 2, 3 vectors and you combine them, you can get like an antisymmetric rank 2 4 tensor. The reason why it's antisymmetric is because if you do the math, you see that like matrices that are antisymmetric need to have like 6 meaningful numbers, which is 2 times 3, because full matrices will have like 16 numbers and symmetric ones will have 10 numbers. So it can only be like an antisymmetric matrix, which is a bit of fun like combinatoric stuff that you can do. So a bit about what are all of the implications of this sort of thing. Essentially, previously separate quantities are now mixed. When you talk about Newtonian mechanics, time is, even though it's part of the Galilean group in the description, it's just a parameter that we use to describe the universe. It's not like a really fundamental thing. So we can keep a lot of our like more time-dependent stuff separate, like energy and momentum. But now, because of the way that boosts are structured and the fact that boosts heavily mix space and time with each other, we can't talk about energy and momentum as separate things. If we want to continue to talk about the universe with things that have well-behaved transformations, we essentially we find out that things that we previously thought were not that related are in fact really, really related. We also have the fact that forces are much more awkward to talk about. You can write a 4-vector version of the force from F equals ma, but it ends up just being really ugly, and it's very hard to like get to separate the forest from the trees when you do that, which is why no one really does. But there are better descriptions of physics using things called Lagrangians that sort of get around this. This is why, essentially, when you talk about like modern physics, which is all relativistic, if you talk about fundamental physics, you don't really talk about forces because forces are just not a good thing to talk about in relativity, because the fact that you have like a good useful 3 tensor does not necessarily mean you will be able to find a simple useful 4 tensor version of it. The 4 version might be ugly enough for you to like not bother to use it in your description and to move to other things. We also have like relativistic versions of old concepts that are much easier to work with, which is why you talk about things like 4 momentum, not to the energy. Like you can talk about it as energy momentum, but it is very much like 4 momentum, because you treat 4 momentum in relativity basically in the same way that you treat regular momentum in Newtonian physics. So essentially, when you learn relativity for the first time, you need to get relativistic versions of everything. Yeah. Okay. So just like as a conclusion of like, if nothing else, when you wonder about like what a tensor is in physics, there's like the meme answer, which is that tensors are things that transform like tensors. But like the underlying truth behind this answer and why it's like actually kind of true is because the transformation properties are the important thing. We have like a lot of redundancy in the way that we can describe the universe. And when it comes to like choosing coordinate system or like notation or whatever, but underlying all of that, on our way to get things that are truly independent of our descriptions, we have like one step before, which is what are the redundancies of our descriptions. And when we have these redundancies in the description, we can transform from one description to another and basically change nothing. And what these redundancies are like limits the scope of like our allowed theories a lot. And the fact that our theories have to like be well behaved under these transformations is more or less how we find them. There is a good exercise that you can do that when it comes to mechanics is like, okay, if we have like these and these and these symmetries in our universe, what are like our allowed theories even? And when it comes to like fundamental theories, like things like gravity and electromagnetism, you get like a shockingly small amount of allowed options, and which is why because invariants are very hard and to talk about like directly because they don't change, so it's kind of hard to like a priori like get them from the description of the universe. You generally want to talk about the things that transform once above that. But the transformations are the fundamental thing. The description is sort of just a notation that you use to get there. Thank you for listening.
That hour absolutely flew by. That was an excellent talk as always.
Thank you. Gabo is typing. You can also come on mic.
Yeah, I think it's going to be easier on the mic. So if the forces are somewhat irrelevant on on relativistic physics, like what kind of, and I missed the earlier talk, so maybe it wasn't said before, but what are kind of the basic rule set that you're using to think about things, like, because eventually like all the Newton principles, they are like the axioms that we use to reason about anything in Newtonian physics, and we don't want to use forces because apparently they're a bother to deal with once you try to combine them and make tensors out of them. But what are the kind of basic rules that you are using in relativistic, like what are the axioms or principles that you're using in relativistic physics in order to relativity like?
Yeah, so there's this. So the more modern way to talk about this sort of thing is what's called analytical mechanics. Essentially, okay. So there's like a lot of detail that you can talk about. You can say that we have like this thing called the Lagrangian, that from it we get the equations of motion and stuff like that. But the essence, in my opinion, of analytical mechanics is essentially we come up with this object called the action. And the action, like all good things in the universe, is a scalar. It's like invariant under our coordinate system. It just depends on our coordinates. And it's like a complicated sort of function thing. And essentially, the action is going to be an integral, like from one point to another point. And okay, so you have an integral from like from one point to the other point, and you want to ask what? Okay, wait, hold on. Okay, wait. Okay, I'm gonna think for like a few seconds so I can like get my words in order.
That's where we need an elevator music.
Yeah. Okay. Okay. To be honest, I would like to give a good explanation for this. And while working on this talk, I realized that that analytical mechanics is probably a good subject for the next one. Mostly because I was thinking about doing quantum mechanics, but I don't know. I think there's like talks about quantum mechanics are like a dime a dozen, and I think that like people outside of the physics field don't know anything about analytical mechanics. I think it would be really good to introduce that. So I'm just going to say that the answer is, I don't think I can like give you a good succinct answer now. So I will give a better answer next time. But fundamentally, yeah, okay, yeah. I'm just going to have my foot in my mouth.
Yeah, because I already had like my next questions because you were talking about an integral, but if you are integrating something in space-time, so in a non-unidimensional space, then how are you decided the walk that you need to take around that space between those 2 points to call the integral? So like I had a bunch of follow-up questions already, so maybe it's better for
this is a bit of a complicated thing. I think that's just going to be what non-physicists 4 is about. I think that would be best.
Already planning sequels. We love to see it. So, in any case, unless there are any more questions, I would like to say thank you again, Monad, for an excellent talk, as always. Then I think we're going to take our final break of today, our second and final break. For another 10 minutes, we'll pick up again at around 4:10, my time. We'll pick her up in around 10 minutes for our final talk today from Hugo, talking about the axioms of choice, which, to quote him, is rambling about math, or maths, as the correct people say it. In any case, chat amongst yourselves, go grab some drinks, and we'll see you all in 10 minutes. Ten minutes past. Yeah, so when Flugo is ready, we can begin again for our final talk today.
Yeah, we can go.
Awesome. Okay. Who's Flugo? In any case, let's get on with our final talk today. That final talk being the axiom of choice by Hugo. Yeah, over to you.
Okay, can everybody hear me okay? Sounds good. All right, so I'm gonna do the wrong thing. I'm gonna have both the banter chat and the question chat where I can see it, but we'll see. So hi, I'm Flugo or Hugo or Unintelligible Noises. So let me write it like this. That's the origin story behind my nickname. So capital H. Yeah. So the way I would say my name is Ugo. So you can make of that what you will. So this talk is going to be kind of rambling.
Hold on for a second. Henrik's having some issues hearing you.
Oh. Well, I can talk about unimportant things in the meantime.
Okay.
So the main point is that this this talk came about. The idea for this talk came about in the math channel. We were discussing, I don't know, Banach-Tarski paradox or something, and non-measurable sets. And somebody said, they've worked in math for half their life and they still don't grok the axiom of choice. And I think, and then I had a bunch of things I wanted to say, and then I kind of just offered to give a DoomConf talk, as one does, because I've learned from River that we're all supposed to give DoomConf talks. And then I wanted to prepare a little bit, but it came about that the talk was scheduled right after the busiest week of the semester, which is fine. But then I haven't fully prepared what I wanted to say, which allows me to kind of retroactively pretend that this was on purpose, because I like the idea that DoomConf talks don't have to be something that's like completely worked out and like all shiny and full of everything, because the whole idea is we like hanging out and talking about things that interest us, and I can kind of do that without much preparation. And I don't know, I want everybody to feel like comfortable giving just impromptu talks about things that they find interesting for however long they want to talk about. And this is how DoomConf began in the beginning, right? So I'm basically retroactively saying that I'm just trying to keep that spirit alive. And everybody's been giving really, really great talks, and it's cool that people have prepared. But I want to fly the unprepared flag here for maybe other people who also want to do that. So the original idea behind the talk, and that's why there's shenanigans in the title, was that I was going to discuss things that happen because of the axiom of choice and things that can happen if you don't have the axiom of choice. But then, as I thought about it for the last few weeks, basically, maybe the points that I really want to make are not so much in that direction, and I'm going to basically subvert the topic for like half or 3/4 of the talk and talk about something else, which is underpinning all of this thing. And it's also, in my opinion, part of the reason why this is such a confusing topic. I think Yeet has an open mic. Maybe if you could.
I just wanted to say that you can segue into your talk whenever you wanted. So.
Okay. Thanks. So what I'm really mostly going to be talking about is hand waving and talking a bit more philosophically about what it means to formalize something. What is formalization? And I have no real formal studies into this topic, basically. Right? I'm not a philosopher, and I've actually never been interested in philosophy until recently when I've basically flipped and almost everything that I'm interested in turns into philosophy. And so these are just my thoughts, and maybe someone has thought about these things much better than I have, and that's fine. We can definitely talk about it. Oh, by the way, one other thing that I want to say is that you can interrupt me to make any comments or any questions or any jokes at any time. Those are not only allowed, but like welcome to them. This will help me. So my main working point here, my main working definition is that formalization means taking something that you want to talk about or want to understand from one setting and trying to put it in terms of something else, maybe in another setting. And when I say it like that, it just basically sounds like modeling, right? And I think that's my point. And I'm gonna be spending some time now talking about why you would want to do that and examples of where that happens. And I don't know, when I was thinking about this through the last few days, I kind of surprised myself in maybe what I see as formalization isn't such a spread opinion. Like maybe it's not such a widespread opinion. So maybe this will be a bit, I don't know, controversial is not the right word, but maybe some people will disagree. And of course that's fine. Right. So the mental picture is that you have some I don't know, X setting and some phenomenon going on here that you want to understand, explain, or whatever. and then you have some y setting where you are going to try to mimic this thing somehow, right, or model this thing. And immediately, because you're changing the context, you're bound to lose something, and you're probably going to have some noise going on this side, right? So things that happen on this side are, you hope they are good enough to help you understand and explain what's going on this side, but it's never going to be an exact match, probably. I'm going to keep saying words like probably and maybe, because I don't want to make it sound like these are extremely fully baked thoughts, right? They're at best recorders baked. But then the point is that, you are bound to lose some details, and maybe you want to lose some details, right? Maybe you're trying to abstract, like Molan was saying in his talk, right? You actually want to abstract away some details, and this can help you understand things. And you can also gain some maybe undesired noise when you do this translation. And I think this is part of the quote-unquote problem with talking about math, because there's a bunch of things. I mean, mathematicians don't really do math for any real-world purpose, but on some level, they are trying to understand stuff, right? And when you go to math, this translation of stuff to math, it is necessarily part of this phenomenon here. So you lose some of the details of stuff, right? When you're talking about two apples and two cars, and then you go to this abstract notion of two, you've lost the car and apples details. And you some stuff comes along for the ride unintendedly, right? And one of these things, for example, is infinity, right? As far as we know, there's no, whatever, right? I'm not gonna make real big philosophical points, but we don't really see infinity in real life, right? There's things that behave kind of like infinite numbers, like the number of protons in the universe or whatever, and they are effectively for almost all effects and purposes like infinite numbers, but they're not like infinite numbers as we have them in math, which I'm going to be talking a bit more about later. And actually, a lot of the weird stuff that happens in math is already because of infinity, and this is I think an underappreciated point, right? Even including the weird stuff about the axiom of choice. They're only really weird when you're talking about the axiom of choice from an infinite setting. Actually, the axiom of choice for finite things isn't even an axiom, as I will discuss just a bit later. So I want to talk a little bit about this x and y thing, but instead of x and y, which is just neutral terms, it's kind of enticing to think of maybe this is some kind of reality, and this is some kind of model. But these words, I don't really want to use very, very heavy words here, so because I'm not really prepared to defend this, on a very philosophical level. And but if you don't like these words, you can just not use them, and you can think of this, more informal on this side, and more formal on this side. Or maybe you can think more intuitive on the left and more technical on the right, maybe. Or, one setting which I want to maybe defend a little bit of where this kind of thing happens is actually when you're programming. Because the reason why you would want to change from X to Y is presumably because you would work better in Y in some way, right? In some undefined way. And this could be because, maybe you don't understand the structure in X very well, and you understand the structure in Y a bit better. Or maybe you had a hand in defining what the structure in Y is. Or maybe, the tools that you're using require you to be in setting Y. And this, for example, could be, you have some real world phenomenon that you're trying to whatever, and you're using a computer to do it, right? And then that already means you must change into this new setting and use this new language and do this transformation from this side to this side, in the hopes that what you're doing on this side will translate back to what's on the other side. And this crossing this divide here, the fact that you are arguing that what you are doing on the Y setting is somehow or somewhat matching what's happening in your desired X setting, these are probably not really what's the word I'm looking for? This can be falsified, right? Maybe it's clear that what's happening on the Y setting is not really doing what you wanted from the X setting. But if it is, it's probably not something that you're going to be able to fully confirm, right? And this will become a bit clearer when I explain some other examples. Okay, so in a way, programming, that's one of the first little controversial claims here. Programming is already an instance of formalization. I had some other examples here. Let's see. Yeah, and in the latter part of the talk, we're going to be talking about, instead of this side being the real world or anything like that, the interesting phenomenon is when you have X equals math and Y equals math as well, right? And that's what you do when you're trying to formalize math using math. But you could do other things, right? So, for example, you could try to formalize math using math and, for example, some kind of dependently typed proof assistant like Lean or something like that, right? This is one big modern project that's going on, and it's really gaining a lot of traction, and it's like plenary talks at the International Mathematicians Congress and so on. So that's another setting. That's another instance of this setting, right? You have math as mathematicians do it all over the world, and with its formal informality all along, and you have this really concentrated and concerted effort of trying to formalize that using this very specific type of language, for instance, Lean. And that's just another instance of this thing going on. Let me see. There's a bit of an elephant in the room here, because when you're formalizing X in terms of Y, that means you're using Y as your base, kind of. But you could also wonder how you're formalizing Y, and then you can use Z for that. And then you could wonder, how do you formalize Z, and then you use W, and so on. And this is kind of inescapable, right? And there's no real hope that this will really end. And it's basically the human condition, right? It's the interesting bit is happening in this interface here, and the game is that we accept Y, and from then we argue about X, and then you can very much play the other game of not accepting Y and then wondering about Y and trying to formalize it in something else. Okay, apparently my camera is not cooperating, but okay, I think we can, just hit me up if you stop hearing me or if you stop seeing the little yellow thing. Yeah, I think my upload speed is really okay. Let's see. And so one more thing I wanted to say in this slide is, and this is a bit about what was happening in the physics talk, is that once you kind of accept this or that you accept it well enough that this cooperation happens between X and Y, then you can use Y to kind of push the boundaries a little bit, right? So for example, I had a slide about this, so I kind of prepared a little bit, right? So somebody shared on the Discord server this talk by CGP Gray. This is from like 5 days ago, the video. And so he was talking about, numbers on runways and how they relate to magnetic North Pole and whatever, and what is magnetism and so on. And he went on to like go and say where this thing comes from on a quantum level, and he was talking about spin, and how these things whirl around and so on. And then his words were, when I say whirl around and when I say spin, you have to understand that these are kind of technical terms that don't exactly mean what they mean in real world, and these are words that we use in math. And really what's happening is, I'm completely butchering the quote, but these are technical things that happen in quantum mechanics, and it's math. And in a way, this is, spoiler alert, in a way this is am I here? Can you guys hear me still?
Yeah, you're fine.
Okay.
You're here.
Okay, good. No, something flashed here. Okay, so the point is, Newtonian physics and so on. This match is kind of clear to see, because you have F equals ma on this side, and then you push something that weighs so many kilograms with so much force, and you see that it accelerates at so much speed and so on. And this match is really easy to observe. But when you go to these more boundary situations like quantum mechanics, you do, of course, the model is based on inspiration from reality, but at some point in your model you have some things that are happening there that you can see happening in the model that maybe you still haven't been able to observe in real life, and then it becomes this kind of theoretical thing, but it's coming from the model, right? It's coming from the fact that you change settings to a setting where you have more control, where you understand things better, and where you can see things happening. And then the hope is, of course, that this is going to continue to match with reality as soon as we are able to look at reality in a better way, right? So, and the final thing that I want to say, I think, in this slide is, again, on the CGP grade point, there's a bit of a problem it's basically a communication problem, where what words you use on either side can be good, but can be confusing if you use the same words, which is kind of what's happening on the spin side of things, right? So we, as human beings, have an intuition of what whirling around and spinning means. And when you transfer those same words to phenomena that are happening in the formal model, you want to carry those intuitions a little bit, because we don't want to use completely new words to talk about things, because we as human beings cannot really do that. It's basically a limitation that we have. So we have to use words that carry some meaning, but we have to be careful that the meaning is only kind of incidental, right? It's only an inspiration. And this is, I think, a very, very big thing that happens with mixing things up, at least in terms of math, right? So I see, I'm a teacher, right? So I see this with my students a lot, right? I write on the blackboard, definition. This natural number divides this natural number when this happens, and then it very, very closely matches with what they have in their mind for what divide means, but it's not exactly the same, right? For example, you could say 0 divides 0 from my definition, but you don't get that from this usual everyday notion of, you divide one number by the other and the result is an integer. So anyway, so this is inescapable, right? So in order to talk about things, we kind of have to do this change of context. And when we do a change of context, we lose some things, we gain some things that we didn't want to gain. And that's the human condition. Anyway, so one example that I wanted to give before going to the axiom of choice thing is, let me just see how I'm doing for time. Okay, I have talked for 22 minutes. That's okay. So one thing that I wanted to quickly say about, before going to the axiom of choice, is there's a famous example in the history of mathematics and computer science, which is the notion of algorithm. Right, so there's this, it's a fairly ancient thing, right? This idea of a method that you apply without needing much inspiration or without needing talent, right? Just following some step-by-step method to go from some input to some solution, right? This this JPEG here is from this Agbobada, right? So this by this guy called Al-Khwarizmi, right? This Persian, I don't know if you can call him mathematician from like 3rd century maybe, where he was, talking about methods for solving equations, right? And one of the methods was this called Agbobada, right? Which was kind of this idea that you can balance both sides of the equation, and if you have 2 times x equals 3, then you can 2 times x equals 6, then you can divide both sides by 2, and then this allows you to find what x is, right? So this is one step, one method. I think this was what was the one called Agbobada, and that's where we got the word algebra. And of course, Al-Khwarizmi is the name where we get algorithm from. And in Portuguese, we even get the word for digit is algoritmo, which also comes from the same name. And so this is a very ancient idea, right? This idea of kind of mechanizing your thought and your methods for figuring stuff out. And this was fine, right? Nobody was really worried about this kind of stuff. And so in a way, this was, let me just delete this page. In a way, this was basically fine on this side, let's say. And then around the turn of the 20th century, we were a bit less satisfied about that, because this guy, Hilbert, he had this idea of formalizing math for his own reasons. And he was a very influential mathematician, probably the most influential mathematician at the time. And one of the things that he wondered about was, we have this somewhat clear notion in our heads of when a formula follows from other formulas, right? For example, if you want to know whether the formula P follows from the formulas Q implies P and Q, that's, yes, I think it's easy to accept that does follow. But then if you make things a bit more elaborate, this question becomes a lot less clear. And so then he wondered, when he put out this question around, 1918 or so, whether there could be some kind of method for just looking at the formulas that in the input and deciding whether, yes, the concept, the thesis follows from the hypothesis or not. And it was not exactly solving this problem, but it's very much related. In the late 20s, this guy called Kurt Gödel, he basically, in a sense, he was proving that this was not. He was proving another thing, but it's very much related, and I'm not going to go into much detail about this. But then, because he was trying to prove that it was not, that such a method could not exist, this creates a much bigger problem, right? Because if he was trying to prove that, yes, such a method existed, he could just do the algebra thing, or, equivalent, and just give a method, and, people would accept it or not as some kind of intuitive step-by-step procedure that worked. But, it would just be math, right? People would just accept it or not accept it or whatever. But once you're trying to prove that something does not exist, then it's a bit more difficult, because, on the informal side, proving positives is kind of okay if everybody accepts that your informal argument works. But proving a negative is a different beast. And then that is one of the situations where you actually need to have a formal definition of the thing and say, according to this formal definition, it cannot exist. So one of the things that Kurt Gödel did in his famous incompleteness theorem was basically proposing a formalization of what it means for something to be computable using this is a modern word, right? For something to be, for you to be able to do something following some kind of formal procedure. Okay, I'll take it. And it was actually, then there was some contribution by Jacques Herbrand and in how this should be done. And Herbrand is one of these kind of unsung heroes. He died very young, and he had some major contributions, but he's not as well known as he probably should be. And Gödel and Erman, they did this in a kind of axiomatic way, right? So you say, oh, you're talking about functions of natural numbers. Say, a constant function necessarily has to be one that you can compute using this sort of method, and some other kinds of functions. And if you have two functions that you already decided you can do in some kind of method, then their composition you can also do in some kind of method, and so on. So they follow this kind of axiomatic approach. And for them, let's talk about Gödel. For Gödel, this was a very kind of a technical definition that he wasn't even very satisfied with, but whatever. And then, a few years later, Church was trying to talk about this Hilbert problem, right? It's called decision problem, or Shenanigans problem. And he also decided to formalize this idea using, in terms of something. And the way he did it is in terms of higher order functions, or in some kind of syntactic notion of higher order functions. So functions that can take other functions as input and produce other functions as output. And he invented this little language, and he used this symbol because it was the one that was available on his basically typewriter. And then, inside of this, in this world, he found a way of modeling natural numbers and modeling functions of natural numbers. And it's a cool little idea. I mean, we're Emacs users, so this is part of our ancient history in a way, because the idea is that you can model, or you can represent the zero-ness, right, the abstract notion of zero, concretely in the system as the higher order function that takes a function, takes an input, and doesn't apply the function to the input at all, just returns this input. So applies the function to the input 0 times. And then 1 is, well, it's a higher order function that takes a function and returns the function that takes an input and returns the function applied to the input once, and so on. And the whole point of this is that, if these are your so-called numerals, right, these are your formal representations of your numbers, then you can actually do some cool stuff with this, right? You can define, for example, what it means to multiply two things. And I didn't give the definition here. I just copied this from somewhere because of time. But the point is that you can write out an expression, like something similar in these terms for a multiplier, or multiplication. And then if you give it two of these formal things, for instance, 2 and 3, and you just work things out, following the rules of the system, which I haven't given, but which are kind of natural. In the end, what you get is the thing which takes as input a function and returns a function which takes as input input, and then applies 6 times the function to the input. So this is the representation of 6. So in our little system, we have managed to represent multiplication. And and then he had this definition of, a function of natural numbers is going to be computable by some method if it can be represented in my little syntactic system in such a way that this thing happens. And again, it's a completely technical definition. It worked for his purposes, which were showing that the Shenanigans problem was not solvable. But in a way, I think he was also, Gödel for sure wasn't, but also, I think Church was also not completely satisfied because this match between what we wanted and what we got isn't so clear in this case, right? I mean, why the hell should it be that this little syntactic game models what we think about following a method, right? It's a very big claim to make. And then it was independently. It was published the same year, but done a bit after actually, but without, as far as we know, without any knowledge. Along came Turing, and he decided to model, also solving Hilbert's decision problem. He decided to model this idea of following a method by really something that really closely matches with that in a technical way, right? So he decided to define, in terms of math, a machine that follows a procedure, Turing machine. And here, this connection between real world and technical world is much clearer. It's much more easily accepted. And then there's the clinching philosophical point is that these three systems give the same motion technically, which really makes it appealing to say that, well, they must be capturing something about real life, and that's where we get it, right? So in this setting, these red arrows are called the Church-Turing thesis, right? Something is computable in some loose sense, if and only if it can actually be computed by a Turing machine, or if it's a closed term of the lambda calculus and so on. Okay, so that was the big preamble. I don't have much more to say, but I wanted to say a little bit about this thing where if you have math on this side, so let's say all of math, and you have math on this side, so some of it. So this is the problem of formalizing math. So you want to find some little system of math where you are somehow able to model all of math. And so the motivations for this are, as I've said before, right? So maybe this little system of math is something that you understand a lot better for some reason, or you have some more control, or whatever, and you want to formalize this thing. Not as far as I know. And so historically, the most successful attempt at doing this is this system called ZFC. I say Z, even though I have more of an American accent, but just because that's how I've mostly seen it said when I was in grad school, and it just stuck. So in ZFC, what you have, so the sum math here is trying to capture the notion of what a set is. And of course, this is already an instance of a loaded word, right? So you have a notion of what a set is, like some collection of whatever, and that's not the notion of set on this side, right? So the notion of set on this side is just a technical thing, right? So it's a male of fried chicken, and it's the chicken is a big issue here. So what is set theory? So the idea is that you're trying to mimic everything that happens in mathematics in terms of this one little system, this one little notion, which is basically, so a model of set theory is going to be something that has points. Let's say. And a relation between these points, right? So this guy points to this guy, this guy points to this guy, and this guy maybe points to this guy as well. And so the idea is that the points are going to be the sets, what we call sets, and the arrow relation is membership. But so just I hope the final time that I stress these words don't really have a meaning, right? The meanings that they have are going to be determined by what we demand that they satisfy. Right. So, and we have, I was going to say 9 axioms, but I'm going to be a bit more precise and say 10 axioms that basically restrict what we are talking about. So the first axiom is that in any model of set theory, there has to be at least one point, right? And this is usually given. This is usually a given in mathematical logic, right? That the structures are non-empty, but okay, we aren't paying by the axiom, so we can just demand it. It doesn't matter, right? So there's at least one point, and then there's the 9 other axioms that are called the axioms of ZFC set theory. And I'm not really going to go over them because that's not really the point. But I wanted to stress what is being done here, right? So what we want to do is we want to capture or formalize or encode everything in math in terms of just this little setting. So it's a big challenge, right? So one of these points you hope you can call the real numbers, and it's going to behave enough like the real numbers that you aren't really losing anything by doing this, or not losing anything really important, really. And another one of these things is going to be somehow something that you call the number 0 and something that you call the number 1. And they have very precise encodings in this setting because they must, right? This is just a formal system. And I get a bit hung up on when people say, oh, the number one is this thing, which is the encoding is this, right? So basically the set which has one element, which is 0, which is the set that has no elements. But again, this is, in a way, this is just an implementation detail, and it's not really the point of what we're trying to do here. Right? The point that we're trying to do is that these 10 axioms that we're going to demand that these things satisfy, are enough to mimic everything that happens in math, right? Including, I don't know, a continuous function on the reals that changes from negative to positive must have a root somewhere in the middle. This must be a theorem that you can prove in your little system about these little objects here, right? So you have the real numbers being some point here, you have some function f being some point here, you have a notion of what it means for this to be a continuous function just in terms of points and arrows and everything. And you know, the big kind of surprising thing is that this matches pretty closely, pretty well, as far as we know. It's very much not an exact match. We know that there's some things that we are interested in talking about here that we cannot talk about here, and these things do exist. For instance, category theory is something that exists here that cannot really be formalized in here. And okay, that's something that we care about. But you know, there's also other things that we care about. Oh, so there's a question about category theory. Is that it? Yeah, so that's because the point is that category theory talks about things that are too large to fit in this setting. For example, the category of all categories, that it just cannot exist in ZFC because of issues, because of ZFC issues, basically, right? So, for example, in ZFC, we know that there cannot be a set containing all the other sets as elements. And in a way, that's kind of the thing that should have to happen if you could model category theory. Yeah, so Nano is asking the question of whether there's a set of things which cannot be expressed in ZFC set theory, and note that this is close to a circular question, right? Because if you want, you know, you can try to formalize what it means to say something in ZFC, right? That's a mathematical statement. So if you can try to formalize it within ZFC, and then within the model of ZFC, you can say, oh, this thing that represents something can or cannot be said in ZFC itself. And there's things that you can do in that direction, but there's a bunch of limitations and theorems of logic which say what you can and cannot do in that setting. And there's just no way that I can go into details about that. So finally, about the axiom of choice. So first, I wanted to say something a lot less controversial. For example, if you don't have any axioms, basically, let's just say you just have the non-empty axiom, right? So this is a model of that theory, right? Because, well, yeah, there's nothing. It is non-empty, so that's fine. So, and there's no other demand. So this is a model of that. Is there? I mean, maybe this is being a bit ambitious, but is there a notion of union of sets in this model? So let me draw some arrows. Let's make this a bit more interesting, right? So when I draw this arrow, what I mean is that A is a set with one element being C, and let's say B is a set containing one element, D. Is there a set that is the union of A and D? Maybe we can get answers in chat. No, right? And that's just it, right? So if you don't say that every pair of sets must have a union, then you just don't get it. And that's part of what it means to axiomatize something, right? If you are interested in a setting where unions of sets exist, well, you better demand it, right? Because otherwise you're not going to get it, unless it follows from other axioms, but it won't follow from just this axiom, right? So then if we put another set here, and we do something like this, well, now you do get it, right? Now it's true that for every pair of axioms here, for every pair of sets, sorry, there is another set which behaves like the union of the two sets that you started with. And also now this is a model of non-empty plus union. Yeah, so Pandemic is asking what the, so there's two questions. Pandemic is asking what the benefit is, and yeah, you know, it's a bit of a philosophical question, right? You when you put something that's more general in terms of something that's more specific, you gain something, right? You gain some understanding of what's going on, because you know this more restricted setting, you just have better structure. You just understand what's going on better. And when you put things that are more general in terms of something that's more specific, you usually gain some understanding by doing that. I guess that's my not very committal answer. Gagbo asked how to get A union B. So what's A? A is a set that only has one element C, and B is a set that only has one element D. So what we want is one set that has elements C and D, and that's E. So E is the union of A and B in this setting. Right, so being an element of is just this guy points to the other guy. Right. So in this model, we have 5 distinct sets. 2 of them are empty, 2 of them are unit sets, and 1 of them has 2 elements. Okay, and finally, about the axiom of choice in these final few minutes. The axiom of choice is just another one of these situations, right? So we have a bunch of other axioms that say what you can do and what you cannot do. So there's a power set, etc. And some of them get very technical, because without them you cannot do what you set out to do, which is mimicking what happens with the notion of set in this formal setting. That's basically the entire game, right? We have this intuitive notion of what a collection is, and we want to mimic that formally, just enough that we can formalize everything that actually interests us from the world of math. So these 3 axioms are definitely not enough, and then you add a few more. You know, and then at some point you reach some technical dead ends, and there's two famous ones. One is the axiom of replacement. The axiom of replacement is basically just saying that if you have something that you have decided is a set, and have something that you have decided is a function whose domain is that set, then you must also have something that is a set, and that is the range of that function over that set, the domain. So that's called replacement, right? So if you have a set and you use a function to replace every element, then the result must also be a set. And being in a set is this technical thing, right? It's a point in your universe with the elements that it must have. Right? So it's a point in the universe, and all the elements are points in the universe, and they all have arrows pointing to that guy. I'm sorry. And then the axiom of choice is really just another one of those technical things. It doesn't have to be, in my opinion, such a big deal, because it's just something that if you don't demand it, then you don't get it. and this is a statement that's actually a technical statement, right? We have logical theorems that say if you don't demand the axiom of theorem with the axiom of choice, then you actually have models where the axiom of choice fails, so it's not a consequence of the other axioms. And then you know, maybe non-measurable sets doesn't exist. And we actually have constructions that give this. Obviously, this takes 2 years of grad school to figure out, but these are known things. Okay, and then. So the axiom of choice, it has this sort of story history, right? So Zernello, so Z in ZFC, he wanted to, for him there was this, well actually it's Cantor, but also Zernello, they had this idea of ordering a set to do recursion. So actually the main original point was doing recursion. Okay, I'm going to make a comment about Nano's comment soon, because that's also an interesting question or comment. But the point is that you want to do recursion on your sets. And, I'm not going to go into extreme detail here, but in order to do recursion on a set, well, you need to order the elements in such a way that you can do the recursion in that order. And it turns out what you need for recursion is something called well ordering, which for finite things is not an issue, but when you get to infinite things, it becomes an issue. And well ordering just means that when you're in the middle of doing something, you have the set of things that you have already done, and well ordering just means that there's a clear next thing that you still haven't done, and that's all that is. And it's very clear why that's what you need for recursion, right? There's always a next thing that you haven't done until when you finish. But until you're finished, before you finish, there's always a clear next thing to do. And the Cantor and Zermelo originally thought that this was just a principle of thought, right? It's just a natural thing. But then it was figured out. It was clear that this doesn't actually follow from the other 8 or 9 axioms, and this is just something that you have to demand. And this is the original version of the axiom of choice. Like every set can be well ordered, so you can do recursion on it following that order. And then with the recursion, you define the things that you wanted to define. But it's not a consequence of the other axiom, so you just have to demand it as an axiom itself, and that's the C in choice, because they recouched it in other terms, and that's a technical thing that I'm not going to go into, right? So the axiom of choice has a million different versions, right? And, it's one of the little badges of honor as a mathematical logician when you figure out your own equivalent of the axiom of choice, and it's a rite of passage. But it's just about this. In the end, or originally, it was just about this, right? Just about doing recursions on your little sets, and then if you demand that you can do it, then you do it, and then you move on. So well ordered. What well ordered means is that if you have a set and you take a subset of it, such that the complement is not empty, then according to the order, there is a minimal element in the complement. That's what well ordering means, and it's basically exactly what you want to have in order to define a recursion, right? So you have this construction going on like this abstractly, and then at some point, some abstract point in time, you have the set of things where you have done the construction, and the set of things where you still have to do the construction. And what well ordering does is gives you a canonical next guy to do the construction. Yeah, so about Nano's comment there. So there's one of the axioms is called foundation, and what it basically says is that this relation here has no cycles, right? So there's no sets containing themselves like this, and there's no shenanigans going on like, oh, C belongs to A, and A belongs to B, and then B belongs to C again. So it's just saying that this is a DAG, right, a directed acyclic graph, and it's just again, really, it's just a technical thing, and it helps you a lot. And if you do this, then the entire universe has this really nice shape where things come in layers, and this helps you a lot with what you're trying to do. But you can also just do without it, actually, and there's some theorems that say that if something is a theorem of ZFC using foundation, then if you do the correct technical massage, then you can also do it without foundation. And there's a question by Gagbo, where is there an axiom that says that you can reduce all the set theory problems to problems working with what's R set, or R as in real numbers, and empty set as a base for the ABC placeholders there. Yeah, so actually you don't even need the real numbers, right? So you're just starting from the base. This is one of the cool things about ZFC, is that just starting from this guy, from this set called empty set, and then forming, on the next level, forming this set, right? And then on the next level, forming the subsets of this guy, and then on the next level, taking the subsets of the what, and then just iterating this process, you get every set, actually. So really, in this formal way, so you get this called this V hierarchy, and then in this formal setting, the real numbers, if you look at it, it's just something completely insane, like whatever. It's just formed of curly braces and empty set symbol and commas, and that's the definition of the real numbers. So that's one of the crazy things about ZFC. Right? It's just one of the also. And so I don't know. So just really coming to the end of the talk here. So the axiom of choice is not usually put in terms of the well-ordering principle these days, right? There's a bunch of different ways of doing it, but one of the ways is that if you have a set whose elements are non-empty sets, right? So if you have a set X whose elements are all non-empty, then there must be a function which has domain X, and whose range is some set containing exactly one element from each of the elements of X. And it's, if you can parse what I just said, it's kind of something easy to accept, because X is some family of non-empty sets, so each guy has one element at least, and then you just form a set taking one element from each guy. And it's a very, I don't know, in my opinion, it's a very intuitive thing. It's not really a big issue. However, when you consider that set is a technical thing, it's just a point in this model, and being an element of is pointing to some other thing, then it's just not a given that this has to hold, right? Just like with the union example we had before, right? So if you have this setting, as we had before, well, then this is just not a model of the union axiom, that every two sets must have another set, which is the union. And it could just very easily happen that without the axiom of choice, your model, has X in it and all its elements and everything is non-empty as you decided. But this guy, this guy, is just not a point in your model because you didn't put it there. And the axiom of choice is just about putting this guy there. And the final sentence is that as I was saying in the beginning, with all of the other axioms except for the axiom of choice, you get several versions of this, right? So if X is a finite set, which is something with a technical definition, then you actually can construct this guy using the other axioms. Each axiom says, oh, if these things are points in your model, then this other thing must also be a point in your model, and then you can kind of recursively construct this set that you must have. However, if X is infinite, then unless you demand that it be there via an axiom, you're just not going to get it. And that's basically it. So Gago is asking if the curly brace expression of real numbers would make real numbers a countable set. Well, only the way I wrote it here, right? Because I use these ellipses here to hide the details, but no. Eventually, the only base element that you demand in usual ZFC is this guy. The other ones are only sets containing sets containing sets containing sets containing sets, which eventually just contain this guy. That was just the point I was making. You can put more things in the base here. That's called set theory with atoms. But in terms of what theorems you can prove, they're basically the same. I think I had something else to say, but I forgot. So I think I can basically stop here. So eventually, if there's more interest, we can talk about axiom of choice shenanigans. Just one thing that I want to say is that so I've been selling this idea that it's just something that you need for sanity's sake in a way. But there's a bunch of things that without the axiom of choice would be really, really weird. For example, we have in mathematics, we have this idea of a size of a set, or of two sets being of the same size, right? This is called cardinality. And the idea is that if you can have a function from set A, which takes different elements of the set A to different elements of the set B, then this gives an intuitive notion that B is at least as large as A. And then if you have also the other way around, some function taking different elements of B to different elements of A, then intuitively this should mean that the elements of the size of A is at least as much as the size of B. So if you have these two things, then they must have the same size. And this is, I don't know, I think this elevator pitch is kind of believable enough, right? This makes sense. However, if you don't have the axiom of choice, then you can have two sets that you cannot compare by size. And this creates a bunch of weird little problems that you just didn't imagine would happen. Or there's a bunch of different weird stuff that can happen without the axiom of choice. And there's a bunch of weird stuff that can happen with the axiom of choice, especially because of infinity. So, there's nowhere to run to, right? It's just going to be weird. And the fact that it's going to be weird is unavoidable, right? It is going to be weird because you're moving to some different setting. And that necessarily brings along some noise and some weird details and so on. And the only hope is that this transformation is useful, right? That's the main thing. Can you use this to do something that you're interested in? And that's basically the entire point of the thing. Okay, I think I'm done. I think I talked for just about as much as I promised and just a little bit more. I think I just completed 1 hour, so I think I'm pretty happy. Hey guys.
Thank you, Flugo. That was an awesome talk, like always.
It was very good.
Yeah. And with that is our final talk for today. But won't go anywhere because we'll probably be sitting around and talking for a little bit. Well, a lot of us are. If recorders want to stop,
Something weird is going on here. I can't stop screen sharing.
There we go. If recorders want to stop recording, then they can, unless is that Beeper Booper wants to do a talk, then feel free to. Yeah, thank you to everybody thank you to the people who have helped record this thing and help plan this thing. DoomConf wouldn't be able to happen without you. One final housekeeping. If people do want to do a talk, then you know where I am, at me. I'm giving you explicit permission to at me. Hopefully we can do a DoomConf September. So if you have any ideas, don't be shy and just talk to me if you don't want to do it eventually. Otherwise, we can sort that out. And yes, welcome to all the new people who have showed up. Hopefully you do stick around for the rest of them. Anyway, I'm done talking.
Yeah, and of course, everyone should give a hand to Yeet for doing all the administrative work to organize the conference. It probably wouldn't really exist without his effort. So thank you very much.
Yay! Putting some method in the madness.
To be honest, my method is mostly madness. So
I think that's how you can keep with it, I guess.
To be honest, my method is just one big org file. So in any case, I think, yeah, if recorders want to stop recording around now, that's fine. And we can discuss how we deal with everything in a minute. But yeah, again, thank you all for coming and enjoy the rest of the conf.